My name is Tabaria. I'm 16 from Bellevue, Washington.
My name is Catherine, and I'm 17. I'm from New York, East Harlem.
I'm Emma. I'm 16. I'm from Los Angeles. Debris. Snow interactions is
what our
focus presentation.
We tried.
So basically, we got this picture from Google Maps, and basically shows Mount Baker. It's a glaciatic volcanic peak. It's 10,781 feet high. Our project is, we did a project on the lower eastern glacial, where the dot is at.
So we spent a lot of time on the glacier, and we got a chance to look around and see everything, how beautiful everything was, and all three of us took a notice of the topography of the snow on the glacier. So we kind of focused on this main question, which is what is the role of debris and solar radiation on snowmelt? This is important because rocks and dust and soot, like possibly even from human pollution, can affect the melt of snow on the glacier.
Even enhance it.
This is us doing the experiment on Mount Baker. That's us starting to dust some plots and Catherine writing down some information. And that stick in the background is an ablation stake. As you learned from the prior presentation, ablation is the melting at the end of the glacier. So the ablation stake is used to measure the melting of the glacier and the snow. And that's to be dusting the snow with some local dust, literally just from those rocks right there.
Okay, so this was the plots that we set up for our experiment. We set up 4 plots, all 50 centimeters by 50 centimeters. We kept one controlled as can be. I mean, it was exposed to all of like the environmental conditions like wind, sun, dirt, whatever. We have the second one was lightly dusted with snow, which is like the most accurate because that's what generally Mount Baker looked like. The snow was lightly dusted with debris. And you can see in the picture like there's still some pockets of snow coming out. This one was more thoroughly coated with dirt and dust. But even though it was like evenly coated, it was only a coating of 2 centimeters. The last one was covered with rocks, and in the middle of each of these plots we had sensors which measured, the temperature every minute. It was really accurate. We put it in 10 centimeters deep, right? Because of the ablation stake that Emma was talking about. We had it out for a day, and in that day we saw a melt of 10 centimeters, so that's how we decided how far we should vary it. Do you guys want to see it? Sarah, I got you. Okay, so from the plots, took a wild guess. I mean, we originally assumed that the rocks would be the ones to melt the quickest because they were the heaviest, they were the darkest, and like generally rocks were warmer around the area. It just made sense. It was just a wild guess, but apparently from what we can see from the graph, this is a graph of the temperature change. It was in change over time, so this is over 24 hours, and then this is over degrees Celsius. And from night to like, for the bare snow around 7 in the morning, everything was maintained at 0 degrees Celsius, which is snow temperature. But already at like 7, the temperatures were starting to fluctuate for the bare snow one. And as you can see where it started to spike up, that was when the sensor got closer to the surface as more snow was melting. Weird, that wasn't our first guess. But we assumed that all the debris would help melt it, but this one was the first to melt, and like the most. And then the second to melt was the coating of 2 centimeters, the like evenly coated one. That one was the second to melt and like the quickest out of all of the debris covered one. And then in general, like generally looking at the dusting and the rock, they behaved similarly in that how they melted and at what point.
Okay, here basically that was like our end results. It showed that our control experiment, it melted less compared to the other plots, and these two, the rock and the dust, they were similar to each other because it dropped down like towards to a similar level. And the one that had a more impact was this one right here, this plot, because it dropped down to 20 centimeters.
Yeah, that was the coated one.
Okay, so here is a little depiction of the bare snow, the control, and the sensor underneath it. The sun's rays were able to heat the sensor because the snow is not very tightly packed like glacier ice. It has, air holes to go for the heat to go through, and while the light reflected and the surface didn't melt as much, the sensor became heated the most because there was no barrier in the way to absorb the heat from the sun. And so here we have the barrier of rock. And so it's like a conductor, and it doesn't let the heat get to the sensor as quickly as if there is nothing there.
That explains the data on the ground.
So we basically learned that the white snow reflects more light and causes it the reflection, because of the color, causes it not to melt as quickly. So you can imagine you're out with your friend Margaret and you're jogging. It's a nice day, you're jogging. And you and your friend Margaret are jogging. And she's doing great. She's just jogging along. She's wearing a white shirt. And you look down, you're wearing a black shirt, and you're having a really tough time. It's like really hot. And you don't know why. And then it's because your shirt's so dark it's absorbing all the light, and you're like 10 times hotter temperature-wise than Margaret, because her shirt is reflecting the heat of the sun. So that's basically the first idea.
Margaret, all right. Second, we learned that a coating of debris will melt more than just bare or dusting because of the conduction of heat through the debris. So conduction, think heating up your stove and then stupidly placing your hand on the stove. The stove conducts the heat to your hand. Conduction.
Oh, jeez. Okay, so what we also learned is that the thicker the debris, it insulates the snow more from melting. And you can think of insulation as like you're sleeping in a sleeping bag. It's warmer inside, and outside is colder. And basically, insulation helps protect the cold from getting from the inside. Getting inside the warm area.
So it would be reversed because the rocks were protecting the snow from warming up from the sun. So like opposite sleeping bag. That was the ablation stick I was talking about. This is how we decided how far deep to bury our sensors. But later we realized, if you look closely at the well forming around the ablation stake, you'll see that there's a well forming around the ablation stake. Taking account of this, we realized that the ablation stake isn't of top quality because it's metal. So, as we talked about before, conductivity, metal is superconductive, and it melted around it, not only like deep, but as well as around. So that also affected like how much, on average, the snow melts. This wasn't an accurate portrayal of how much the snow melts. Okay. On that note, we had our second experiment. We looked into how the colors and shading of light versus dark rocks play into snow melt. We have these rocks here with us today, carried them up the mountain just for you guys. Blackie is my favorite. He's the darkest, and he's named Blackie.
Basically, what this graph shows, in the y-axis, there's temperature in degrees Celsius, and the x-axis, there is time. We recorded our data in the morning, morning, noon, and evening, and the lighter rocks shows that they had a more subdued response than the darker one. The darker ones had a more dramatic change in its temperature throughout the day.
And we measured the surface temperature of the rocks with this infrared thermometer.
If I could just science for a second right now. I thought it was really cool because like once you get up in the glaciers and like the mountains and start doing science, you start to see science, right? So once we had these data charts, hold up you guys, I swear this is good. You'll notice the middle one is always the highest, like for all of them, even though like these were subdued responses and these were dramatic. That's because like noonish, afternoonish is when the sun is at its highest. So it like melted, it like increased temperature the most. Science.
This is called first order science. First order science, yeah.
So some more about wells. That rock, pass it around, you all should get a look at it. It's very light colored and circular. This is the well it made after one day. It's just a round well. It's not very deep, but these are some other wells made by rocks the same day. Over the same amount of time, the rocks are darker and the wells are deeper and larger because of their size and the darkness, but they're hotter. This is a well after more than one day. It's extremely deep and a lot wider than the one day wells.
Okay, so taking those wells into account, on a larger scale we have bedrock in the background and we have snowfield, and you'll see in the middle there's this giant rock which could like represent the little tiny pebbles we used of like pictures we took. The rock created that well there, but as it was creating this well, you'll see that this snow is darker than this one. That's because this well that was formed also created a trap for dust to like fall in, and we learned in our prior experiment that dust helps with the melting process. We also took the average temperature over this area, which was really cool because I thought it was a long process and it was over this giant plot, and we took temperature every 3 steps. We got this average of 28 degrees and we were really close to the end, and I was like, why are we still doing this? It's 28 degrees, I promise. And then as we were getting closer to the bedrock area, the average temperature started to increase, and it was 30 degrees, so we're like, what's up? And then we realized over the bedrock, we took the average temperature of that area, and it's 95. And there was these moats that you can't see here, but like you'll see like sort of right there, that formed between the bedrock and the edge of like the snowfield. And that's why the temperature increased while it was getting closer to the bedrock, because the bedrock was like giving off heat and melting the snow as heat melts. Yeah.
Okay, so what we concluded is that solar radiation and inclusion, right? Debris and conduction, they both play a role in the snow melting. However, the results varied as like the thickness of the debris. Oh, the results vary because the thickness of the debris and its properties play a very important role.
Oh, you push it.